Okay, hello everyone. We meet again in general properties of transition element. Alright. So for today, okay, I will focus on the form colored compound. Okay, I have some question here. Okay, why are some substances colored? Okay, while some are not. Okay, let me show you. Okay, actually the color of complex compound can be readily explained in terms of crystal field theory. Okay, crystal field theory. Okay, here I use some example of complex ion, okay, which is hexa, aqua, titanium 3 ion. Okay, so now for electronic configuration of this complex ion is argon 3d2 and 4s2. Okay, and then since this titanium, this central metal is used of titanium 3, so we must write down the electronic configuration of titanium 3 plus. So it consists of 3d1. Okay, for electronic configuration, okay, for titanium 3 plus, since it consists of 3d1, so it's located one unpaired electron in this 3d orbital. So for this 3d orbital, okay, you must know that for each orbital it have its own name. Okay, so the first one, it have dxz. Okay, the second orbital is dyz. Third orbital dxy. Okay, and then dx square, okay, minus y square, and the last one is dz square. Okay, and then for the first three orbital, okay, which is dxz, dyz, and dxy orbital, it is located in between the axis. Okay, located between the axis. So we call these three as a non-axial orbital. Okay, non-axial orbital. Okay, while for the last two orbital, okay, dx square and dx square minus y square and dz square, okay, these both are located, okay, in the axis, right, in the axis. So these both we call as a axial orbital. Okay, one more thing, in isolated complex, okay, in isolated atom, okay, we can see that this transition metal ion, the 3d orbital, okay, are in degenerate orbital. So this we call as a degenerate orbital, which is degenerate orbital is a same energy. Okay, right? So before the presence of ligand, so this central metal ion must draw, okay, must drawn in degenerate orbital, which is same energy. Alright, okay, in exam, okay, you must draw the energy level diagram, okay, by put the arrow lah. Okay, right, next one. Okay, under influence of ligand in a complex, the 3d orbital are split into two groups with different energies. Okay, which is we call this as a non-degenerate orbital. Okay, let me see. Yeah. Okay, so here is the crystal field ligand, which is for the first one. Okay, for the first one, this orbital is in a degenerate orbital. Okay, degenerate orbital. Okay, with the presence of ligand, so with the presence of ligand, which is there is a repulsion between electron in the ligand and the electron in the d orbital of the metal ion. So that's why this repulsion causes the 5d orbital split into two with different set, which is 2 orbital is a higher, okay, 2 orbital is a higher, okay, 2 orbital is a higher, okay, and then the 3 orbital is a lower energy. Okay, so this is we call non-degenerate orbital. Okay, so for example, we have a titanium aqua titanium 3 ion. So we located the D1. Okay, D1 in a first d orbital. Okay, when the presence of ligand, which is H2O ligand, so what happen is repulsion occur and it will split into non-degenerate orbital. So we must locate the electron in a lower energy first. Okay, so what happen is when exposed to light, okay, electron in lower group of the orbital will absorb certain wavelength of visible light spectrum and it will get excited or promote to the higher group of the orbital. Okay, what happen is, okay, when it absorb the wavelength, okay, the presence of the light, so what happen is this electron will excited to the higher energy level. So, okay, and then this energy difference between the two sets of the orbital correspond to the wavelength of visible length. So, for this thing, okay, it consists of different energy. Okay, during excitation occur, so it will form energy difference between the two sets of the orbital, which correspond to the wavelength of the visible light. So it will absorb light here. Okay, it will absorb light. Okay, so and then what happen is uh, okay, and then after it absorbing the certain wavelength of visible light, okay, so the complementary color of the color that is absorbed is transmitted. So and then it will transmit, okay, it will transmit the color. So color will be transmitted, which is we can see the color. Okay, we can observe the color appear, which is the complementary color from the absorbed color. Okay, so for different color result, when certain portion of light is reflected, transmitted or absorbed the visible light after hitting a substances, so the reflected light give color of the substance, which is this color is the color transmitted that we can see the color form, right? Okay, so this is we call as a DD transition. So this is the DD transition. So this DD transition is responsible for the color of transition metal compound. So this is we call as a DD transition. So during this excitation. Okay, now I give two example of complex ion, which is the first one is a hexa aqua copper 2 ion, and the second one is tetrachlorocuprate 2 ion. Okay, for the both complex ion is have different coordination, which is the first one is a octahedral complex. Okay, while for the second one is a tetrahedral complex. Alright, for now I will show you the first example, which is octahedral complex. Alright, okay, for the first one, okay, I want to show the electronic configuration, okay, of the complex ion. Okay, since both of complex ion are using the same central metal ion, which is copper. Okay, so for copper, okay, copper 2 plus. So what is the electronic configuration? Okay, become argon, okay, 3d9. Alright, okay, so for the first one, okay, we must fill up all the electron in the degenerate orbital, okay, which is before the presence of ligand. So it have 9 electrons, so we just put the electron here. Okay, 1, 2, 3, okay, 4, 5, 6, 7, 8, and 9. Okay, as we know that the electron, the orbital diagram, okay, for the first orbital is dx, y orbital, and the second one is dx, z orbital. The third one is d, okay, yz, okay, and then the fourth is dx square minus y square, and the last one here is dz square. Okay, this is the type of orbital present in 3D orbital. Alright, okay, for this complex ion, okay, so the ligand that use, okay, in form the complex is a water. Okay, water we name it as a aqua. So when the aqua is present in the central metal, okay, what happen is, okay, automatically the degenerate orbital will become splitting into two orbital. Okay, so for the for the degenerate orbital here, okay, here is we call as a degenerate, okay, orbital. So with the presence of ligand, it become non-degenerate orbital, okay, which is different energy. Non-degenerate means that different energy level. Okay, so then, okay, what happen is, okay, when for octahedral, okay, we can see that the axial orbital, okay, the axial orbital are repulsed to the higher energy level, okay, which is for these two, okay, for these two electron, it is the d, okay, x square, okay, minus y square, and also the, okay, z square orbital. Okay, so this axial orbital is we call as a Eg level. Okay, and then for the lower energy, it is the non-axial orbital, which is dxy, okay, dxz, and dyz orbital. Okay, so for the lower energy is we call as a T2 T2G level. Okay, T2G level. Alright. Okay, so for this non-degenerate orbital, okay, this is for octahedral. Alright. Okay. But now is how to fill up the electron. Okay, since I use the weak ligand here, which is water. Water is a weak ligand, weak ligand. So we can fill up all the orbital in the all the electron in the orbital. Okay, so starting from lower energy 1, 2, 3, okay, and then 4, 5, 6, 7, 8, and 9. So this is how we fill up the electron in the non-degenerate orbital. Okay, so now, okay, when they have sunlight here or white light here, okay, what happen is, okay, the electron in lower energy, okay, electron in a lower energy, they will excited to the higher energy. Alright. Okay. So, okay, this is cause the presence of, okay, the presence of energy different. Okay, energy different. And as we know that the energy different between the two set of d orbital, okay, between this d orbital correspond to the wavelength of visible light. Okay, which is for this copper 2 ion which bonded with aqua ligand, okay, it form the, okay, it will absorb the orange light, okay, which is it will absorb the orange light, okay, orange light, okay, so it will absorb, okay, it will absorb, okay, the orange light here, okay, and then okay, as we know that when we it absorb the orange, okay, what is the complementary of color that will be transmitted? Okay, so this is the blue color. Okay, so it will, okay, appear blue. So this is the color that we can see, okay, in a naked eye. So that's why, okay, refer to the copper 2 ion, okay, which is the complex ion here. That's why, okay, the colored complex is become blue color, okay, because of the complementary color transmitted from the absorb orange color. Okay, so this is how the color form. And okay, The most important, okay, what is the transition called? This is the D transition, okay, which is when, okay, electron in a lower energy is being excited to the higher energy. So DD transition occur, and this DD transition occur, okay, will form the colored for the complex form. So that's why for the hexa aqua copper 2 ion, we can see it as a blue complex. Alright, so this is the octahedral complex. Okay, we back to the second complex ion, which is tetrahedral. Okay, so now, okay, for the second one, okay, for the second one, you can see that it also use the copper 2 ion, so we must fill up the electron, okay, in the orbital. Okay, same, 1, 2, 3, 4, okay, 5, 6, 7, 8, and 9. And the orbital type also same, okay, starting from D, okay, XY, okay, until the Z square orbital. Okay, now, okay, for tetrahedral, alright, okay, when the presence of ligand, okay, in the central metal ion information of complex, what happen is, okay, the non-axial orbital will be repulsed to the higher energy level. Okay, how to memorize it? So tetra here means that 3 orbital as a higher energy level. So tetra, 3 orbital upper, right? Okay, so that one you must memorize. Okay, so now, okay, so this is the XY orbital, the XZ orbital, okay, and the YZ orbital, okay, which is non-axial orbital, and this is the T to G level, become higher energy level for tetrahedral. Okay, why for the lower energy level? Okay, this is the X square minus Y square and the Z square orbital as a lower energy, which is this is the EG level. Alright, so for tetrahedral cases, I also use the Whitfield ligand here, which is chloro. Chloro is a Whitfield ligand, so we can fill up the electron in the lower energy level orbital and also the higher energy. So starting from lower 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, so this is how we fill up the electron. Alright. Okay, in the same time, okay, what happened when the presence of the sunlight here? Okay, once again, okay, electron in a lower energy level will excited to the higher energy level. Okay, during this excitation, okay, so it will form energy different, and we know that this energy different, okay, correspond to the wavelength of visible light. Alright, and for the wavelength, okay, for the copper here, okay, it will absorb the red color. So it will absorb the red color. Okay, it will absorb the red color. Okay, and what is the complementary of the red color? Okay, so we can see that it will appear as a green. Okay, it will appear as a green color. Okay, it will appear as a green color. Right? Okay, so that's why for the uh, tetrachlorocuprate 2 ion, it is appear as a green complex. Okay, because of this transition occur. Okay, so what is the name of this kind of the excitation? Okay, when electron from the lower energy is excited to the higher energy, okay, what happen is we call that DD transition occur. Okay, so DD transition is being occur. Okay, and what happen when the DD transition occur? Okay, the complex become colored. Okay, the complex become colored, which is for tetrachlorocuprate 2 ion, it will appear as a green color. Alright, so I hope that you will understand for this part.